So good afternoon, everyone. Let's present myself again. So I am Nora Dada from the Laboratoire Mécanique of Lille in France. So today I will present you one part of my work, which is the influence of the casting process of one aluminium alloy in high temperature and under fatigue loading. This study is investigated by in situ X-ray thermography and digital volume correlation. Yeah. So my presentation is divided in 4 principal parts. First one is the context and the objective. The second part is around the experimental protocol applied on fatigue test at high temperature. Then a characterization of microstructure. And finally, analysis of damage mechanism. So this study is about aluminium silicon alloys used in cylinder heads. The cylinder head is submitted to several thermomechanical stresses. Indeed, during the start-stop of the vehicle, the temperature is from 20 to 250 degrees, which leads to the sorry. How to have the problem? Sorry. Which leads to the crack in the fire zone of the cylinder head. And recently, the manufacturing process had changed from the conventional die casting to the lost form casting in order to optimize geometry, reduce cost, and control consumption. But this change has a main disadvantage, which is the microstructure. Like, as you can see here, the microstructure is coarser with more defect. The size of the different phases inside the material increased in this material. So the aim of this study is to understand the influence of the casting microstructure on damage mechanisms in high temperature and during low cycle fatigue. So for that we developed an experimental protocol. The first step is to extract flat specimen from the cylinder head. Then you need to select a good specimen. What I call good specimen, it's specimen with all the defects, all the porosity in the area of observation, which is the central zone here. For that you use laboratory X-ray microtomography, and thanks to this tomography image, we can characterize in 3D the microstructure. So then we perform in situ fatigue test in high temperature. And finally, we can observe the quark recession and quark propagation in 3D, thanks to digital volume correlation. So the in situ fatigue tests were performed in the cyclotron ESRF at Grenoble in France. For that, we use a voxel size of 2.75 micrometer, and the scan lasts about 40 seconds. Here, it's the furnace. Furnace is composed by 4 halogen lamps. And this furnace is around the fatigue machine here. So if you see the in situ observation details, you took an image at the minimum load and at the maximum load, then we perform some cycle and so on. After that we can have the reconstruction of the volume, and from that we can compute full field measurement in 3D. This full field measurement was possible thanks to the natural tracer inside the material, which gave a good contrast. For the correlation, we used a YADIC software developed in the Laboratoire Mécanique of Lille, and for that we used a size of element of 4 voxels. The correlation was performed between the minimum load and the maximum load of each cycle. So let's now see the result. We first the characterization of the microstructure, and here it's the pore distribution. So here we see the 3D rendering of pore in all the specimen, and you notice clearly that the majority of pore has a size around 20 micrometer, and the maximum size of pore it's around 1 millimeter. This pore is a microscopic edge with a tortuous shape, and you see here that all the pores are very different shapes. So what else we can find in this material? There is hard inclusion, which represents a volume fraction of 17%. So here you have the silicon phases inside the aluminium matrix, then the aluminium copper phases, which is more shiny, and then the iron intermetallic phases. We see that for the silicon and for the iron intermetallic phases, they have a highly interconnected network in 3G. Whereas for the copper here, it's not so interconnected, but they have a complex structures. So you see from this characterization that this alloy has a really complex microstructure. So to understand the damage mechanism, we did some post-mortem analysis. So here I show only one part of the fracture surface, and we superpose the decohesion and fracture surface. So what they call fracture, it's when the particle is broken, and you can see the particle in the both sides of the fracture surface, and decohesion only on one face, on one side. So for the aluminum, copper, and iron particles, it seems to have fracture in the middle of the particle, the blue one, and after decohesion. But for the silicon particles, we see clearly there is more decohesion than fracture, because silicon is different networks, it's like fibers. So when the fibers are parallel to the loading direction, there is fracture of the particles, and when they are perpendicular to the loading direction, we have decohesion, and this decohesion have a higher volume than fracture. But from this post-mortem analysis, we cannot know if it's decohesion or fracture happens first, and we don't know the strain level of each particles. So you need to perform in situ fatigue test. So from in situ fatigue test, we can understand the damage mechanism. So here, the initiation mechanism. So this is topography images at the minimum loading and at the maximum loading of the first tensile loading. So here you see that at the maximum loading, the crack initiates close to the pore, and we notice that for all specimens, the crack initiates always close to the large pore, and always during the first tensile loading. Once the crack initiates to the pore, it propagates in the hard inclusion silicon, iron, and aluminium copper phases. But what you see another phenomenon, which is microcracks in the phases here. So we have a lot of microcracks, and all these microcracks after will connect to create one big porosity, and which leads to the final fill. So if you continue to the propagation mechanism with SEM image now, so this is SEM image around the final fracture, and here far away to the final fracture. So you see in the both cases there is this microcracks in the phases, but you see clearly it's more above all in silicon phases, as you can see here. We can explain why it's more in silicon phases, because silicon phases has an extensive network in all the volume. It represents the majority of volume fraction, but also this silicon phases have a coarser microstructure which create large stress concentration around these particles. And above all, these particles are more brittle than the other hard inclusion with high temperature. That's why you see more microcracks in silicon. Now, if you look at the strain field analysis, so here is strain field cycle by cycle. At the first cycle, after 10 cycles, and after 30 cycles, just before the failure, the final failure. So here you see that the crack localization corresponds to the crack strain localization corresponds to the crack initiation, and then here you see the strain localization between large pores, which correspond to propagation, and here all the micro cracks between the pores. If you look at this image at the end, this in blue represents the pore at the reference image before any loading, and behind it's the microstructure just before the failure. So you see well that these two pores are now connected. So there is well a coalescence of all the micro cracks in high temperature. So to complete this work, in this study we can understand the influence of the calcium microstructure on low cycle fatigue mechanism, damage mechanisms in 3G in high temperature. The tomography, 50% tomography image allow to understand the damage mechanism and also to characterize the material in 3G. And the digital volume correlation helps to understand the relation between initiation site, crack paths, and local microstructure features. So we can say that the crack initiation is porosity driven, so in the area where there is enough strain concentration, while the crack propagation is along hard inclusion, and in this case above all in silicon phases. Now we are trying to study the local strain for each phases in order to predict the strain, the level of strain just before the failure. Thank you very much for your attention.